Now let's look at an example, shall we? We've got a blue 4 kilogram cart initially moving to the right with a speed of 6 meters per second, colliding and sticking to a red 8 kilogram car initially at rest. What's the final speed of the two cart combination? Initially, only the blue cart has momentum, right? Because to have momentum, you have to be moving. So if you're at rest, you got no momentum. So 4 times 6, 24 kilograms times meters per second. We don't have a nice short way to put this, so we can just call the units Scopetus, right? Or not. Kilogram times meter per second. Finally, the two carts move together, but we can treat them as a single 12 kilogram object. Because we don't know the system's final velocity, we can just say that the final momentum is 12 times v. So it's just in terms of the velocity. So it's okay that we don't have numbers. It's kind of uncomfortable for you. And I get that. Don't be too afraid of it. It just means 12 times v, whatever v is. Set the initial momentum equal to the final momentum. So here we have it. The initial momentum of the blue car plus the initial momentum of the red car equals the combined masses times the final velocity. 4 times 6 equals 12 times v is what we will get. So 24 equals to 12, and we can see the final velocity is obviously 2 meters per second. What happened here? Did you see the two carts end up moving 2 meters per second? Here we go. So it's less velocity than that blue car initially had, but more velocity than what the red car had. So that's it. This is just how it works. We can take conservation of momentum. We can make conservation of momentum diagrams for the situation. Note that we put 0 over any momentum that is 0. So just so you don't get confused, you can just write in a big old 0 over the velocity for the red car, or the momentum chart for the red car. The blue car has a mass of 4 kilograms, and it is moving with a speed of 6. So 4 times 6, and then you shade in each one of these, and you get 24 kilograms times meters per second. No momentum for the red car, and then finally the final one. The total mass is 12, so even if we didn't know the speed, just by using these charts we can kind of figure out what the speed is. So it's 12, and then 12 times what will get the equation equal to 24. What type of collision is this? Different types, remember? So to find out, we calculate the total kinetic energy before and the total kinetic energy after, and we'll compare it. For the blue 4 kilogram car moves with a speed of 6 meters per second. So the kinetic energy, which is 1/2 mv squared, and we plug in m and v, we get 72 joules. After the collision, then the masses are combined. So we have one 12 kilogram object moving with a speed of 2 meters per second. So 1/2 mv squared gives us 24 joules. We've lost a good amount of energy. Momentum is conserved, but energy is not in this case. So what has happened to the energy? It's been dissipated to the environment, heat, sound, light maybe. The energy is less than the energy before, so the collision is an inelastic collision. In fact, since the objects stick together, we know without any kind of calculating that the kinetic energy is lost and the collision is perfectly inelastic. That only happens with a sticky collision. The crashes together, sticks together, and moves as one object. Perfectly inelastic. Here's another one. 1 kilogram cart, initially moving to the right with a speed of 6 meters per second, crashes with a 2 kilogram car initially at rest. As a result of the collision, the blue car comes to rest. What's the speed of the red car? So initially, only the blue car has momentum, and its momentum is 6 kilograms times meters per second. And then after the collision, the red car is the only one with momentum, but we don't know the speed. So we would say the final momentum is mv equals 2 times v. Set the initial momentum equal to the final momentum. Initial momentum of both objects equals the final momentum of both objects. 3 meters per second. Here we go. With the cartoon. There you go. Red car ends up moving 3 meters per second. Conservation momentum diagrams for the situation. Again, there's not a whole lot of difficulty here. You've got 0 for the red car before the collision and 0 for the blue car after the collision. What type of collision is this? To find out, we calculate kinetic energy. Is it conserved? Before the blue car moves with a speed of 6, so the kinetic energy equals 18 joules. After the red car is moving with a speed of 3 meters per second, which is 9 joules, we've lost a bunch of energy, so we know it's inelastic. The collision is just inelastic, not perfectly inelastic because the two objects don't stick together. A red 4-kilogram cart, initially moving to the left with a speed of 6 meters per second, collides with a blue 2-kilogram car initially at rest. As a result of the collision, the blue car moves left at 8 meters per second. What's the final speed of the red car? Remember, momentum is a vector. In any vector, you need to take into consideration the direction. If something is moving left or down, remember about that negative, right? Feels like it's been a while. Initially, only the red car has momentum. Its initial momentum is m times v, which is 4 times negative 6. So we get a negative momentum of negative 24 kilograms times meter per second. Finally, both cars will have some momentum because both are moving, but we can't treat them as a single combined object because the carts might be moving differently. Did not say the carts stuck together. Normally in a problem, it's going to be very explicit in saying the two objects combine masses, or the two objects stick together, or the two objects end up being stuck together, or moving as one. Something like that. There's our conservation of momentum equation. All the momentums before equal all the momentums after. And we get the final velocity of negative 2 meters per second. Here we go. Now the red car's speed is a lot smaller. The blue car is obviously a lot faster. It goes up to negative 8. Up to negative 8, right? Conservation momentum diagrams, we can do this. The mass, 4 units this way, 6 units down because it's negative velocity. And then down because it's negative velocity. Down because it's negative velocity. What type of collision? Look at your kinetic energies. Before, we've got 72 joules. Kinetic energy is only positive because velocity is squared. So even if you have a negative velocity, negative 2 times negative 2 is still going to be positive 4. After the red car moves with a speed of negative 2 meters per second and the blue car moves with a speed of 8 meters per second, red's kinetic energy is 8 joules, blue's is 64 joules. 64 plus 8, 72 joules. So this is an elastic collision because all of the energy was conserved. System starts and ends with the same total kinetic energy.